We're going to go ahead and take a look at sampling distributions of proportions now. So it's going to be a similar idea. What happens when we think about taking multiple samples over and over again? This time, instead of a sample mean, we're looking at sample proportions. And then what does the central limit theorem apply here? How does it apply here? And so when we think about sample proportions, again, that comes from a quantitative variable, meaning that again, we're looking for a proportion or percentage of something. So to start off, we look at this first example, okay, and we revisit binomial distribution data because that's from a binary, right? You have two outcomes, yes or no, success, failure, right? So in this example, we from group of 30 students in a stats class, we record the grade received at the end of the course, okay? And so we suppose the distribution looks like this: 15%, 34%, B's, 30% C's, 13 D's, 8% F, right? What would the distribution of number of B students for this class look like? Okay, so now when we think about this and we look specifically at the number of students who get B's, right? That's 34%, right? We're assuming, of course, we have to assume independence, right, in this situation. And so what we would be looking at, N is 30. The probability of someone getting a B is 34. So what would we expect to see, right, out of 30 students? We would expect 10 of those students in a class of 30 would expect 10.2, approximately 10, with the standard deviation 2.59. So this information here helps set us up for thinking about a sampling distribution for proportions, right? Proportions instead of counts, right? Proportions give you, right, the percentage, right? The p hat x divided by n, right, as we think about that. Now, we're going to use this idea, right, this idea of a sample proportion to estimate a population proportion, right, and thinking about its distribution, kind of like what we did in example one. You have a mean, expected value, and a standard deviation for 30 students. But imagine now, like if we looked at another 30 students and another 30 students, right, over and over again, it leads us into the central limit theorem for proportions. Now, we have to consider again certain questions about how large is large enough for a sample to be normal. Now, with a categorical variable, when we're looking at proportions, we're looking at n times p, right? The number of successes has to be greater than 10. N is the sample size, p is the probability for success. N times q, or n times 1 minus p, has to be greater than 10 too, right? The complement of success is failure, that's your q. And so as long as that, then we can assume the distribution is going to be normal. So in a situation where we have 19% of people wash their hands after using their toilet, okay, this is pre-COVID. If you surveyed 50 random people, right, and remember 19% wash their hands, we would expect only 19% of them to have washed their hands, right? Now, to analyze the distribution using thinking about the central limit theorem, right, is the sample size of 50 large enough to use the normal distribution? The answer is, well, we have to check the number of successes and the number of failures. N times P is 9.5, so it's close to 10. We're pretty close. N times Q, 40, the number of failures, right? So we're, again, just checking that condition that the sample size is large enough so that we can assume that the distribution is normal. Then we can analyze it through normal probability situations. So in this case, the conditions would be met, right? Let's think of the same situation. What if our sample size is 75 random people who exited the restroom? Is this large enough? Yeah, it is again, because 75 times 19, 75 times 0.81, the conditions are met to assume we can use a normal distribution, right, to analyze the situation because of the central limit theorem. Now,